In this lesson, we're going to talk about the fundamental theorem of calculus. As the name suggests, this is very, very important topic. As far as theoretical understanding is concerned, I think the fundamental theorem of calculus is the most important topic in calculus altogether. At least that's my opinion. In terms of computation, I'll regard this one as number 2. Number 1 is chain rule, narrowly beating out the product rule, number 3. In any case, we are talking about something very, very important. We need some warming up, however. Let's review antidifferentiation just a little bit. So here are trivial antiderivative rules. 0 for constant. Antiderivative of sum is sum of the antiderivative. Coefficient can come out. The power rule, logarithmic function, exponential function. Here are a little bit more extended form, which I regard highly important. Instead of just usual power rule, if you put ax plus b linear function in there, then the same power rule structure stays, but we need 1 over a. Here's the reason. If I start from the right hand side and take the derivative, k plus 1 will come out and you're going to multiply that, consequently killing up this k plus 1 in the denominator. But that's not all. By the chain rule, the derivative of the inside, which is a, that's going to be multiplied, and consequently cancelling out this a. So this a in denominator is necessary in order to undo the chain rule computation. The same is true for k equals -1 case. We have this 1 over a for the same reason, for the chain rule. For exponential function, again we have 1 over a for the same reason. Here are the derivative rules, antiderivatives rule for trigonometric functions. Again, please note that the recurring theme 1 over a, 1 over a, 1 over a, 1 over a. Some more tangent and cotangent functions, and then some square functions, and then some inverse trigonometric functions are here. I usually do not write inverse trigonometric functions in Calculus 1, so I de-emphasize them in gray, but in Calc 2 I probably will have to. Let's talk about definite integrals now. If I say just integral, that usually means definite integral. I'm going to use the term antiderivative rather than indefinite integral. Definite integral can be expressed in more precise terms through Riemann sums, and that's going to be done in 5.2 and 5.3, I think, of our textbook. But I usually cover them in Calculus 2. Here, I'm going to concentrate upon a little bit more practical aspect in 2 ways. Number 1, graphical explanation. Number 2, in terms of application. Here's graphical explanation. The definite integral is a signed area. So we have a graph of a function y equals to f of x, and this vertical line x equals to a, and that vertical line x equals to b. So the definite integral from a to b, f of x dx, is the signed area. Here's the rule. If my function is positive, so the graph is above the x-axis, then we take the positive of this area. If my function is negative, and consequently the graph is below the x-axis, we take the negative of that area. Adding them all up, we get a signed area. In this particular situation, blue part seems bigger, so the overall quantity will be positive, but of course not always. Another way to explain the definite integral is through accumulation, and then we're going to talk about in the properties. But actually, let me tweak the order a little bit. These properties are easier to understand because they are coming kind of hand in hand with anti-differentiation rule. Coefficient can come out, great. Sum of the definite integral, definite integrals of the sum is a sum of the definite integrals, just like anti-differentiation. Now here they are. These rules are unique to the definite integrals. Let's talk about this. If I start and end at the same x-coordinate value, then the definite integral is 0. Here's a visualization. We may have a function, but the important part is x equals a to x equals to a. Right here, this vertical line segment, because that's when x equals to a. So instead of having a region, we have a line segment with 0 length. So what's going to be the area? Of course, it's going to be 0. Next, this one is talking about applicational side of the definite integral. Definite integral is basically an accumulation. So definite integral from a to c all the way is the same as definite integral from a to b, this brown part, plus the definite integral of b to c, the purple part. So definite integral from here to there, from a to c, is an accumulation of everything. So this brown part and blue, this purple part added up together. If this curve is, for example, the daily profit of your business venture, for example, then definite integral stands for your accumulated profit in 3-year period or 1-year period, whatever that will be. And of course, accumulated profit can become negative if your business is not doing very well, so it should be a signed area. The final rule, if I flip a and b, is the same as putting minus sign. Why is that? We can deduce it from the first two rules, from b to a and then a to b, and apply the second rule, then we're going to get integral from b to b. But that's 0. So what do you have? First integral plus second integral equal to 0. So second integral is equal to minus of the first integral, or vice versa. So remember these 3 rules, especially the second one. That's going to be very useful in calculating the definite integral. Okay. Now that we talked about what the definite integral is, and then we talked about some property, let's talk about the fundamental theorem, which will allow us to do the calculation. Instead of trying to measure the area, we can calculate the definite integral using the antiderivative. That's what this fundamental theorem is talking about. It simply gives you the relationship between differentiation and the definite integral. So definite integral a to b f of x dx is equal to capital F of b minus capital F of a, where the capital F function is the antiderivative. The fundamental theorem of calculus actually has 3 parts. One is this: if my function small f of x is continuous, then the definite integral exists. Number 2, in that case, when small f is continuous, then antiderivative capital F exists. And then third is this relationship between one and the other. Number 1 is the hardest. Number 2 is not as hard but still very hard. And then number 3, this formula itself is not too difficult to prove, but what's the point? So I'm going to regard this as just a formula. The proof of the fundamental theorem is usually covered in real analysis, probably real analysis 2, I think. 3610, I think. Now that we went through definite integral and the fundamental theorem of calculus, let's do a couple of exercises to calculate the definite integral. Let's calculate this definite integral. How do we do that? Well, let's calculate antiderivative, capital F of t, and plug in t equals to 1, plug in t equal to 0, and subtract one from the other, just like what this fundamental theorem says. But I want you to get more used to the practical notation here, which I'm showing right here. So we have definite integral, expanded just like usual antiderivative computation, and then use the power rule to find out antiderivative. And then here's the notation: bracket open and bracket close with this 0 and 1. And then this bracket with 0 and 1 is a shorthand of the next step. I'm going to plug in 1 and I'm going to plug in 0 and subtract 1 from the other, just this right hand side part. If you do that, you're going to get this computation. Not difficult. We have plenty of time, so let's go over to next example. Again, we have definite integral, but the idea is antiderivative computation, and then we're going to plug in 9, plug in 1, subtract 1 from the other. We're going to use bracket notation again, and here it is. Integrand can be re-expressed by splitting up the numerator. We have done this before. And then the first term can be expressed as a power form, and the second term again another power form. Now, we use the power rule to find out the antiderivative of the first and the second. And this third step would have been the end of the antiderivative problem. But this is definite integral, so we have to do one more. We have to use the fundamental theorem of calculus, and that's this bracket notation. Plug in 9 and plug in 1. The starting at 1 and ending at 9, so we have this 1 and 9 in the same places, and plug in 9 and plug in 1 and subtract one from the other. It's just a routine computation using the calculator, and you're gonna get this 44. Well, looks like we have sufficient time to do one more problem, so let's go ahead and do that. Okay, that's a fundamental theorem, and let's do this one. Okay, we have sufficient time, so let's do it a little bit slowly. So how do we calculate this definite integral? The key is antiderivative. So what is the antiderivative of cosine squared? Is it sine squared? Actually, no. Antiderivative of cosine squared requires this trigonometric identity. Oops. Okay, because if you recall the antidifferentiation formulae, there was a formula regarding cosine function and sine function where the inside is ax plus b, but nothing about cosine squared or cubed or things like those. So used the half angle formula or power reduction formula, whatever you may want to call, and then re-express the inside. Now let's move on to the next step. Just another preparation as a matter of fact. Let's manipulate the inside a little bit further. 1/2 plus cosine of 2x 1/2 times cosine of 2x. I think that'll do. Okay, and nothing actually changed here, just it looks better this way. And then let's apply the antiderivative rule. So antiderivative of 1/2 is nothing more than 1/2 x. And then antiderivative of cosine is sine, so we need something like that. And inside stay the same, and then a value is 2, so I have to divide by 2 again. But there was 2 before, so we need 1/4. And after doing something like this, it's gonna be a good idea to check your answer through putting into by taking the derivative. And then let's go with this bracket notation, which means I'm gonna plug in pi and I'm gonna plug in 0 and subtract one from the other later on. So let's go ahead and do that. Plug in x equal to pi. What do you get? Pi over 2. Oops. Pi over 2, and then 1/4 sine of 2 pi. But sine of 2 pi, that's going to be 0, so that's going to be pretty good quantity. Now let's plug in 0. What do you get? Plug in 1/2 times 0, so that's 0. So 1/4, and we have sine of 0. But sine of 0 is 0, so we have a bunch of zeros here. And sine of 2 pi is 0, and 1/2 times 0 is 0, 1/4, and the sine of 0 is 0, so the answer is just pi over 2. It'll turn out that this integral is going to be necessary whenever circles arrive. Actually, it'll turn out that if you calculate the area of a circle and with appropriate parameterization, you're going to end up with something like that.